MEI Statistics Minor, Bivariate Data 3, Lines of Regression. 3.1, Calculating a line of regression for random or non-random data. So regression analysis is a process for estimating relationships between variables. You will only be expected to investigate a linear relationship between two variables. However, regression does extend to curves and between multiple variables. So a regression line is a more mathematically rigorous line of best fit. In actual fact, you could consider a line of best fit to be a visual estimate of a regression line. The regression line you'll be using is called the least squares regression line. You'll find out why it's named that in video 3.3. But other methods for regression lines also exist. This is the simplest one and the one you'll be expected to use. So when the data is random or non-random, it's only appropriate to calculate a regression line when the data is roughly linear. So this one, non-linear, no. This one, yes, but we'd recommend you remove the obvious outlier. Try and track down why that error occurred. Try and track down why that outlier occurred. This one, despite it only having one outlier, it's not an appropriate experiment for linear regression, because if we remove that, then the value of whatever is along the x-axis is fixed. So there's not going to be a relationship between the two. It's just going to have y that is varying between these values. X is not doing anything. So there is no linear relationship between x and y. This one, probably we can see that there is kind of a linear relationship going on, but the errors are large and so the result may not be that accurate. Example 1 has raw data. So Simon performs an experiment where various weights are attached to a spring and the length of the spring measured. The results are given in the following table. Those of you who have done mechanics may recognize this as a Hooke's law experiment. So the mass here is being controlled by the experimenter, so it is non-random. The length has a theoretical true value for each mass, but still will have an element of experimental randomness to it. So this is our random variable. If I put the data in Geogebra here, I can come over to this button here, go down to two variable regression analysis, tell it to analyze, and it will draw a scatter diagram for me. You can clearly see that there is a linear relationship there. And in actual fact, Geogebra will do the job for us. If we go down to this bottom section here, choose a linear regression model, it will draw our regression line and tell us the equation right here. Y equals 1.91x plus 21.31. Now you can do the same thing on your calculator. When you're using your calculator, it's very important that the non-random control variable goes on the left-hand side, as it is here, and the random variable goes on the right. If they're written the other way around, you're going to need to switch them. Then you need to use the two variable statistics mode, and you may get an output that looks something like this. Y equals a plus bx. It will almost always be in terms of x and y, and then it will tell you the value of your coefficients. You then have to combine that information together to write down the equation that we're looking for. We're probably going to want to use m for mass and L for length, and in the calculator the left hand row is always the x and the right hand is the y. Our y, which is our length, L, is going to be equal to 21.3, rounding to a sensible degree of accuracy, plus 1.91 m. You might similarly have another question that looks at summary statistics. So here we are actually given our variables m and l, and we are given the summary statistics. And you'll notice it's exactly the same summary statistics as we had for Pearson's product moment correlation coefficient. And they asked us to find the least squared regression line of L on M. That means we want something of the form L equals A plus B M. So again, we're going to have to use our old friends, sex, psi and sexy. And this time, a little bit further down the page, it describes the least squares regression line. It gives you an equation here. And you'll notice that there is an A missing. But they do tell you what B is. The reason is because they've put it in a slightly different form. They've put it in a form that ensures, you'll notice this from your work on straight lines, that that form will ensure that it passes through the point x bar, y bar. In other words, it will go through the point that represents the mean of the two variables. As before, ignore this bit over here, far too easy to make a mistake. Calculate sex, sine, sexy, or in this case, just sexy and sex, and then plug it into these formulae. So there are summary statistics again. Those are the formulae that we're going to want to use. You might also want to make a note that x is the non-random, so it is the mass. So your non-random variable is always x, so x is going to be equal to m, y is going to be equal to L. You might want to make a note of that at the side, just so that you don't make any mistakes. So we first find m bar and L bar. I'd recommend you keep as much accuracy as you can to avoid rounding errors, and use your calculator memories wherever you can. Next we want to use sex to find SMM, plug the numbers in, and use sexy to find SML, then plug in to find B. Now finally, we want to use this form here. We recall that the y is equal to L, so that's going to be L minus L bar equals B times the x is the m, so m minus m bar. Pop all those numbers in. So then a quick rearranging of that and a quick bit of rounding leads us to L equals 0.00609 m plus 2.89. Each of those have been rounded to 3 significant figures. In the next video, we're going to be using that line of regression for random or non-random data.